Hello everybody, today we're going to be talking about the myocyte action potential. The action potential of a cardiac myocyte is a bit different from the action potential that occurs in skeletal muscles. One difference is that the duration of action potential of the cardiac myocyte is about 15 times longer than that occurs in skeletal muscles. This is because we have a plateau phase in the action potential of the cardiac myocytes, which we'll talk about. When the cardiac myocyte gets stimulated either from the conduction system or from flow of ions from the gap junctions from adjacent cells, an action potential will occur in that cardiac myocyte. Before we start, let's talk a little bit about the ion channels that are present within the membrane of the cardiac myocyte. We will begin by talking about the sodium channels. These sodium channels are called the fast sodium channels because they are very quick to open and they are very quick to close. Therefore, they remain open for a very brief period of time, about a few 10,000ths of a second. This channel allows the movement of sodium ions from the outside of the cell to the inside of the cell in this direction. This occurs because the concentration of sodium outside of the cell is way higher than the concentration of sodium within the cell. And as you know, ions move from areas of high concentration to areas of low concentration. These sodium channels are the first channels to open during the action potential, and they are responsible for this rapid depolarization. Because you know, depolarization is basically just a rise in the positive charge within the cell. These sodium channels are very similar to those that are found within the skeletal muscles. So let's review what I just said. The sodium channels are called the fast sodium channels. Those are very, very fast. They open very quickly and they close very quickly, and hence they remain open for a very brief period of time. This is about a few thousandths of a second. But during this few thousandths of a second, huge amount of sodium ions will flow into the cell very quickly, very rapidly, raising the membrane voltage about 105 millivolts. And this is responsible for phase 0, which we'll talk about more in detail. The other ion channel is the calcium channel. Now, this calcium channel is not present within the skeletal muscles. This is called the slow type calcium channel, the L-type calcium channel, or the sodium calcium channel. These calcium channels, in contrast to the sodium channels, are very slow. When they are told to open, they do not open immediately, and even when they do, they close very slowly, so that they remain open for a brief period of time that is relatively longer than that of the sodium channels. It is about several tenths of a second. These calcium channels are what's very special about the cardiac myocytes, because these calcium channels are responsible for the plateau phase that occurs especially within cardiac myocytes. These channels allow calcium to move from outside of the cell to the inside of the cell, very similar to the sodium channels, and it's due to the same reason. Now, the calcium that flows within the cell not only is going to give the plateau phase, it also contributes to the contractile machinery of the cardiac myocytes. So let's review this. Calcium channels, they're either called L-type calcium channels, the slow calcium channels, or the calcium sodium channels. They're slow to open, they're slow to close, and they remain open for several tenths of a second. This is relatively longer than that of the sodium channels. And the calcium that comes in is also responsible for the contractile machinery, and this is in contrast to skeletal muscles, where calcium is only coming from the intracellular sarcoplasmic reticulum and not from the extracellular space. These calcium channels are responsible for the phase 2, which is called the plateau phase, that is very special for cardiac myocytes. And the third type of channel that I want to talk about are the potassium channels. There are multiple various types, and these allow the potassium ions to flow from the inside of the cell to the outside of the cell. This is the opposite of the sodium and calcium channels, and the reason behind that because potassium is mainly an intracellular ion. The concentration of potassium within the cell is significantly higher than that of the outside of the cell, and therefore it will move in that direction. Potassium channels, there are multiple types. They're responsible for efflux of potassium ions. Efflux just means the movement of ions from the inside to the outside of the cell. Potassium channels are involved in multiple phases of the action potential, but mainly is responsible for phase 1 and phase 3. The myocyte action potential is composed of 5 phases that are numbered 0 to 4. Now, I've delineated phase 0 right here, and you can see that it's very brief. This point right here is when the cell gets stimulated, and this is followed by an almost immediate opening of the sodium channels. Now, they remain open for a very brief period of time, and they close right about here. During that time, huge amount of sodium ions will flow within the cell, sharply raising the voltage of the cell. So phase 0 is just the rapid influx of sodium ions through the fast sodium channels. Because of the huge amount of sodium ions that flow to the cell is going to become more positive. Initially, the resting membrane potential is about negative 85 millivolts. During phase 0, this raises to about positive 20 millivolts. This is an approximate rise of about 105 millivolts. Because these sodium channels are so fast, the phase 0 is very fast, it's very short, and it begins when the fast sodium channels open, and it ends when they close. Phase 0 is followed by phase 1, Phase 1 begins when the sodium channels close. Potassium will start moving through the potassium ions to the outside of the cell. Because you have positive ions leaving the cell will start becoming more negative. The voltage will decrease. This is due to potassium efflux, and this phase is called the initial repolarization. So phase 1 begins when the sodium channels close. The potassium ions will start leaving the cell via the various potassium channels. It's called the initial repolarization, and it ends when the calcium channels open. Now phase 2 is interesting because it starts when the calcium channels open. Now calcium channels were told to open right about here. Because they are slow, they only start opening right about here. So it took the calcium channels a period of time, right about this much, in order for them to open, because they are slow channels. But once they open at the end of phase 1, two things will happen. Calcium will start flowing to the inside of the cell, which is a positive charged ion, but also the permeability to potassium ions will decrease. Now this will markedly reduce the amount of potassium ions that are leaving the cells through the potassium channels. And this balance of calcium positive ions entering the cell and the reduction in the number of potassium ions that are positive leaving the cell will result in this plateau phase, where sort of the membrane almost remains unchanged for a brief period of time. It begins when the calcium channels open. They're slow to open. They do not open immediately right after the cell gets stimulated. There's a slight delay. And when they open, the membrane permeability to potassium will be greatly reduced. We're not sure why this happens, but regardless, the combination of calcium ions flowing in and fewer potassium ions leaving the cell will cause a plateau in which there is a minimal change in the voltage membrane. And this is called the plateau phase. This phase is present only within cardiac myocytes and is not present within the skeletal muscles, and is responsible for a more prolonged sustained contraction. Now eventually those calcium channels will close about right here, and this marks the end of phase 2 and begins phase 3. When the calcium channels close, the membrane permeability to potassium will return to normal, and potassium will start flowing out of the cell, and the voltage will decrease until it reaches the resting membrane potential, which is about -80 to -90 millivolts, and an average of -85. So phase 3 begins when the calcium channels close. The potassium permeability will increase and return to normal. The potassium efflux continues until the cell membrane potential returns to its resting membrane potential, which is right about -85. This phase is called the rapid repolarization. And phase 4 is basically the resting membrane potential, and it ends when a new stimulus reaches the cardiac myocyte and phase 0 begins. And this cycle repeats itself. So phase 4 is just the resting membrane potential, about -80 to -90 millivolts, and it ends when new impulses reach the myocyte, which open the sodium channels, and phase 0 begins again. So just a quick recap. Phase 0 is when sodium channels open and positive charges fill the cell, but then they close. Potassium ions will start leaving in phase 1, so the positive charge will decrease, so the voltage will decrease. But then we have delayed opening of the calcium channels, which in combination with the reduction of potassium permeability will cause the plateau phase. But then the calcium channels will close and potassium ions will start flowing out of the cell, leading to this rapid repolarization until we reach the resting membrane potential. And we'll end this with just a few points of difference between the myocytes and skeletal muscles. Slow calcium channels are not present within the skeletal cells, and the potassium permeability remains unchanged throughout the whole action potential of the skeletal muscles. Therefore, they have no plateau phase. Also, calcium within skeletal muscles is coming only from the sarcoplasmic reticulum, in contrast to myocytes, which also uses the calcium that flows from the extracellular space. Now, I hope this has been helpful, and thanks for watching.